Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Werner Heisenberg's 1925 seminal work, Quantum Theoretical Interpretation of the Kinetic and Mechanical Behavior of Atomic Systems, stands as a cornerstone in the evolution of quantum mechanics. This essay delves into the genesis of this revolutionary work, its meticulous formulation, immediate impact, subsequent influence, its critical reception. The intellectual landscape of 1925 was ripe for such a profound reimagining of atomic behavior. Prior to Heisenberg's work, the classical mechanics, successful for macroscopic systems, proved utterly inadequate in describing the intricate dance of electrons within atoms, the discrete energy levels observed in atomic spectra, the photoelectric effect, and the quantization of angular momentum paint a picture of a fundamentally different reality at the atomic scale. Max Planck's introduction of the quantum of action, although a pivotal step, hadn't fully resolved the underlying mathematical and conceptual challenges. Existing models struggled with the perplexing problem of electron orbits and their stability within atoms. This inadequacy spurred a fervent search for a new mathematical framework. Bohn's model, while successful in explaining certain spectral lines, lacked the mathematical rigor to encompass the full range of observed atomic phenomena. Heisenberg, building upon the groundwork laid by Bohr, Einstein, and others, proposed a radical departure from classical notions of causality and trajectory. Central to his approach was the rejection of explicitly visualizing electron paths. Instead, he focused on quantifiable, observable quantities, the frequencies of emitted radiation and the transition probabilities between energy levels. His core concept, matrix mechanics, introduced matrices to represent physical quantities. These matrices, incorporating the fundamental concept of quantized energy levels, were not merely convenient mathematical tools, they embodied the very essence of the quantum realm. He used the commutation relations, specifying the mathematical interplay between these matrices, to define the operators corresponding to physical quantities like position and momentum. Crucially, these operators were non-commutative, demonstrating the quantum world's intrinsically probabilistic and non-deterministic nature. The work itself presented a systematic approach to calculate these transition probabilities and derive the correct expression for the spectral lines. This involved a precise method for constructing the matrices, utilizing a clever combination of the energy level diagrams and the algebraic relations of angular momenta. He devised a method for determining the necessary structure and properties of these matrices to predict measurable quantities, a paradigm shift from the classical notion of calculating a trajectory. He carefully defined the set of rules for constructing these matrices and the operations on them using precise algebraic expressions. The rigor of his approach was evidenced by his derivation of the spectral formulas, a profound mathematical triumph validated by experimental observation. The immediate impact was profound. Matrix mechanics, almost immediately, provided a mathematically rigorous and accurate description of the hydrogen atom and even allowed the prediction of additional spectral lines with unparalleled accuracy. Further analysis yielded remarkably precise predictions regarding the rotational spectra of diatomic molecules. Moreover, the methodology directly connected atomic physics with the burgeoning field of abstract algebra. Heisenberg's work became immediately influential and was swiftly adopted by leading physicists. The concept of matrix mechanics, along with the simultaneous development of wave mechanics by Erwin Schrödinger, led to the rapid development of quantum mechanics. Later, Directives' work further refined the mathematical formulations. Heisenberg's emphasis on observable quantities and transition probabilities profoundly influenced the development of quantum field theory and quantum electrodynamics, shaping the modern understanding of particle physics. His focus on the operational definitions of physical quantities provided a framework for dealing with the profound theoretical paradoxes of the quantum world and the interplay of classical and quantum concepts. Heisenberg's methodology faced some critiques. Initially, a stark departure from visualizing electrons as classical particles was viewed by some as counterintuitive, a criticism particularly voiced by those deeply entrenched in classical thinking. However, the sheer explanatory power of matrix mechanics, its impeccable mathematical rigor, and its ability to reproduce and predict precisely known experimental data soon superseded these doubts. His rigorous mathematical approach became a model. Physicists started using computational methods to solve problems related to a variety of physical systems. The reception, ultimately, was overwhelmingly positive, reflecting the inherent beauty and power of a revolutionary mathematical framework. His approach, although initially challenging, proved to be a robust tool for describing the complexities of quantum systems. leading to deeper insights into atomic behavior. His work inspired generations of physicists and mathematicians, leading to the development of quantum chemistry, quantum information theory, and many more subdisciplines. Within modern physics, Heisenberg's influence on later physics is undeniable. A direct influence on others is clearly stated, and specific examples are available. This included Bohr, who engaged in numerous discussions and collaborations, leading to the further refinement of quantum interpretations and the formulation of complementary principles. This collaboration directly fostered the development of new theoretical frameworks. The development and application of these principles resulted in significant scientific advancement in the field. In conclusion, Heisenberg's quantum theoretical interpretation of the kinetic and mechanical behavior of atomic systems stands as a testament to the power of mathematical formalism in unveiling the mysteries of the quantum world. His profound insights profoundly reshaped our understanding of the atom and paved the way for subsequent theoretical and experimental advances across several scientific fields, including chemistry, nuclear physics, and condensed matter physics. It remains a landmark achievement, exemplifying the transformative power of scientific inquiry.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.